Okay, good morning. As I said, you need to go to the course website and download this pre and post processor and also project planning document. Let me show you. Okay, this pre and post processor is just a zipped file. Okay, let me download that. My computer. It's kind of slow. Were you able to unzip the file? Looks like I have difficulty unzipping it.
I do know that our department computers, or at least mine in my office, cannot do zips, .zips or .rars. They can't do them. It's really annoying.
Okay. Let me try that. Looks like it tried to unzip at the same folder. Let me.
I think you just right-click the folder.
Yeah, this one. Extract all. Okay, now I need to browse to this new folder. Maybe you'll do it. Nope.
Interesting.
Were you able to unzip it?
Yeah,
It's going
yeah,
just
I did.
weirdly slow.
You just right-click the folder.
Okay, let me close that. Right click this guy.
And you can see 7-zip.
Yeah.
Select the 7-zip.
7-zip.
Yeah.
And then extract
To the next one.
extract to
Yeah, done.
Oh, here we go. Really slow.
Okay.
this one.
Yeah.
No idea why it's so slow.
5 minutes.
Oh, okay.
1 meg.
Cool. Okay, now I've finished. All right, let me open that up by file type. There are right now, you can see 4 executable, how to say that?
Executable.
Executable, I'm sorry. Executable files. This first one, Casca, is the preprocessor. You use that to generate the model, okay? By clicking here and there, and specifying the coordinate of the point of the model, not each node of each element node, okay? It's just the geometry, and then you can use the program to generate mesh for you, okay? So that's the preprocessor. Now once you generate that, you run the program, you will get an output file with the extension .imp. It's a text-only file, and that is the input file you need to use for your FEM program. Okay. Now sometimes by looking at just a data-only file, it's difficult to visualize the geometry, whether the mesh is set up correctly or not. So in order to check that, you use this program, the fourth one, the mesh data.exe. You run that file and take the output file you generated with Casca, and it will generate a mesh data output file that will be suitable to as the input file for the post processor, which is called canplot.exe. Right? All right. So this one, Casca, is the preprocessor. The mesh data is a converter that converts the output from Casca.exe to the input file for canplot.exe. And the executable file canplot is for showing the result. So you can plot stress contours, strain contours, displacement contours. Okay? So that's for that. And here the third executable file, FEM demo.exe, that is the executable file that is my program, okay? I programmed it. But I only give you the executable file, so you don't have the source file. You need to do the source file yourself. But with that, you can run a FEM calculation. If you have the right input file, just take that as input file, it will generate result. And the result then can be used to as the output file for this canplot.exe. Okay? And I also provide a bunch of input file from here beam up to here. So a total of 6 input files are already provided to you. You can look at those input files. They follow a predetermined format. Okay? Even though they are 6 totally different problems, but they follow the same input format. So these are the input files. So in principle, you can just run your demo and read each time, take one input file and run it, you get a bunch of output. Then you can use the canplot to plot the result. All right. And the mesh data is one of the output file. It contains the data for doing the contour plot. Okay. Casca.doc is the Casca user's manual. It explains how to use that preprocessor. Okay, and then I provide a quick tutorial here. So I would say, before you read the more exhaustive user's manual, maybe it's good to go through a quick tutorial. So I would do that first. Okay, and then the readme.txt explains what all the files in these folders are. Okay, so all these are necessary. I would start with readme and then do the tutorial, and then run. After you've been through the tutorial, follow the steps here. You should have a pretty good idea what how the preprocessor works and how to generate mesh data for the post-processor and how to use the post-processor. Okay. So that's that. Then I think what may be useful is to provide you a kind of plan. You don't have to follow that, but that's my recommendation. Let me open the project planning document. Okay, project planning kind of use the tools. The tool we use for senior design project, which is the planning phase. Okay. So, because we are faced with a huge project, if you try to tackle it, all of it at once, it seems kind of intimidating, right? So I break down this whole project into some more manageable, smaller tasks. Here is my suggestion. Task 1. Okay, there are a total of, let me see here, 9 tasks, okay? So in theory, if you finish those 9 tasks, and then you will be done with the whole project. The first task I suggest will be learn to use the preprocessor Kazka.exe to generate FEM input file. That seems understandable, right? Straightforward. Okay, the input will be the zip file. I posted at KState Online. Download that. So here are the detailed steps or activities you need to go through in order to accomplish that task. For example, first, certainly you need to download the zip file, right? Unzip it, and then start with README, and then go through the quick tutorial. Because it's a tutorial, you need to follow step by step the description there. After that, you should have a good idea how to use Kazka to generate input file. Then I suggest that you should generate successfully a number of output files using the preprocessor. Of course, after you follow through this tutorial, you should have the output file described in the tutorial. In addition, I suggest you to create 2 additional files. One is a simple square, just one element. The other is the same simple square, but more elements. Actually, I would say 4 elements. Okay, let me draw that. One is this. Because we use Q8, so this will be, you will have 8 nodes, 3 corner nodes, 4 corner nodes and 4 mid-edge nodes. And then later you're going to do a simple problem like fix one end and apply, in fact, not a total fix of everything. You should do it like that. So this node is fixed in X and Y. This node is fixed in X only. This is fixed in only. So it can shrink freely if you like. Then you put a uniform traction here. This is a very simple problem to solve, right? So you know immediately, take the force divided by the cross section, you know the stress by hand calculation, and you can calculate the strain easily and displacement easily. Everything you should be able to calculate by hand accurately. Then you generate this input file, and then later the first run or first problem tested should be this one using your program, assuming you completed your FEM. You output the displacement, the strengths, the stresses, and check with your hand calculation. If the result is your FEM result are accurate in comparison with your hand calculation, then you may have a very good chance that it is correct, but not necessarily guaranteed. Sometimes you may have a program that works for a simple problem like that, but give you wrong result for a more complicated problem. But if it cannot work correctly for this problem, you can say for sure that your program is incorrect. All right, so this is the first problem. I call it the one element model. And then another one will be the 4 element model. The 4 element model, the geometry is the same, but this time, instead of using 1 element, you're going to divide it into 4 elements. One way you may think is just split line here, right? So you have 4 regular square elements attached together, but that's not very good. I suggest you put a node here so that it's kind of distorted. So you will have one element like this, another element like that, and an element like that. The way you purposely put a node not at the center is now you have some element that is distorted. And you can review some of the aspect if there's any error in your program that cannot take care of a distorted element, you will review that. So this is a 4-element model, but of course it's more complicated. And you have this additional node, and then you have all these mid-edge nodes also. So that will be the 4-element model. Now, if your program can calculate correctly the 1-element model and the 4-element model, now I would say your program has a very good chance of being correct. Okay, but you still have a bunch of other benchmark problems to run through. As you can see, the 1-element model tests the correctness of your element stiffness matrix calculation, but because it's 1 element, essentially there's no assembly. So it does not test the assembly part of your program. The 4-element model will test the correctness of the assembling process, right? So that's why this is useful. Okay, so these are the 2 output files you should generate and follow through other steps. Here it talks about using the data to convert the output file into input files for the post processor, and then play with the post processor so you know how to use it. Okay, and I put a suggested duration for those tasks, 5 days. The second task, okay, is programming the reading of input files and writing into the output file. Now we are talking about your FEM program now, okay? And you need to know how to open a file, an existing file, which is input file, and also open a new file, which is the output file, and how to read from the input file and how to write things into the output file. When you do that, these steps is only practicing opening files and writing into files. There's no programming, no FEM program at all. But surprisingly, I found a lot of people struggle with those just file I/O. Okay, so I suggest 5 days for that, and then the next step will be to calculate the element stiffness matrix. And again, the input will be the input file with just 1 element. Okay, use this 1 element example to test your program all the time. Okay. For that, now you need to use arrays. 1D array for load vector, displacement vector, 2D array for stiffness matrix, for matrix. Okay, so that's to some could be a challenging step. All right, that again, put 5 days to that, and then next step will be to program assembling the global stiffness matrix. Okay. Let's say, before you move on to this step, you need to output this element stiffness matrix into a text file, and you should be able to calculate the stiffness matrix using either Maple, MathCAD, MATLAB, whatever, or even hand calculation. At least I will check several elements. The first element, I will check 3 diagonal elements. The first, maybe the 5th, and the last. And also 3 off diagonal elements. Maybe the 2, 1 element, and 3, 4 element, and something like that, okay? To make sure it's correct. Always check after you finish one task, check thoroughly. All right, let's say your element stiffness matrix calculation is correct now, you can move on to assembling. Okay, so this is the task 4. Once you are done with assembling, now you have a global stiffness matrix, right? Now you need to move ahead and do the load vector, calculation of load vector. This is task 5. Okay? And I again list some individual activities there. Remember, use the one element example for checking all the time. And again, put 5 days to it. That brings us to the beginning of May 3rd. Task 6. Now you need to impose essential boundary conditions. Okay? First, I would suggest you just assume it's fixed, which is simpler. You need to impose that before you can solve it. Okay? I think 3 days for that should be enough. And then program the solver. Well, program a solver itself can be a significant task. So to make things easier, I will provide you the solver. So you don't have to spend a lot of time on getting that. The solver I provide you is a very simple Gauss elimination method. It is pretty robust and it works very well for most situations. The difficult part, the program elimination is not so difficult, but we all know that for the Gauss elimination, you need to pivot it correctly because we relied on the diagonal element to eliminate other of diagonal element below it, right? If that diagonal element is very small comparing to the remaining element, and you are using a small number to try to eliminate the other significant ones, it can introduce significant error. So we always do at least partial pivot with the solver here, okay? That's the more difficult part. So I will just provide the solver to you. So your task will just it is a function or a class, you just add that class to your program. But of course, you need to make sure it interface correctly with the rest of your program. So that's for that. Once this is done, essentially, it's done. So you have the correct stiffness, global stiffness matrix. You have the correct load vector. A solver is provided to you. You just solve it. Solving a solution is just take the inverse of the matrix and multiply the load vector, which will give you a solution, right? Which is the nodal displacement. So that's for solving it. Task 8. Program the solver, and then you need to check for multi-element model. Let's say at task 8, you check your 1-element model, it gives you correct result. You check your 4-element model, it gives you correct result. Check the other stiffening, other benchmark problems. Along the way, you may discover more errors that you need to fix. Let's say you were able to finish that. The last one will be to check all other benchmark problems. Okay, if you do it well, you should be able to finish it before the end of the semester. But I advise you to here my planning is the beginning. We start a little bit slow, so you get used to it. But if you find the first few tasks are easy to you, move faster, okay, than the plan. Questions? No? Well, I think that will be it. I will stay here in case you have questions, okay? But you are free to move, to leave.